inviting me to speak here. And so today I will be talking about various aspects of the spectral gap problem, which is one of the main problems of open quantum chaos. I will go around to stating the problem and explaining a little bit the history later. But first I want to say that somehow the more you work on this kind of problems, the more you realize that there are a few components needed to understand to solve a problem like that. And so some components look quite complicated, rather difficult, and some components look extremely simple. And the unfortunate or the fortunate feature of these problems is that the components that look complicated, they're not exactly simple, but they're manageable. So there is technology to understand them. And I'll talk a bit about this technology, but I will try not to go full microlocal in this talk. And the components that look very simple are actually the essence of the problem, and they are the ones that are very hard to understand, at least for me. So this will be an open-ended talk. I will formulate a couple of conjectures and somehow explain why, in my opinion, there are still quite a few things that could actually be done here. So let me start with one of these problems, which looks very simple, but I don't really know how to solve it. So I'm going to restrict myself to the case of discrete Fourier transform so that how my presentation is the simplest. And it turns out that already for this case, things are rather complicated. And in fact, the general case to some extent can be reduced to that one. So I just consider the group Z mod n. I consider the unitary Fourier transform here on L space L2. And then I ask the following question. Let's say I'm given two subsets of Z mod n. I want to bound the operator norm of this product. So I just take the Fourier transform, and I sandwich it between multiplication operators by the indicator functions of these two sets. So 1x, what it does to a function, it simply just erases all the entries except those that were in x. All right. So of course, I'm not interested in this question for just one collection of sets and for one n. So this will be a high-frequency question. So I will let n go to infinity. Assume that I am given some families of sets here. And I want to understand how does this norm grow, or how does this norm decay, really, as n goes to infinity. And the best situation for me would be if this norm decays like some power of n. And the exponent in this power we'll call beta. And in case this estimate holds, I will say that these two sets, or other families of sets, satisfy uncertainty principle. So the problem indeed looks simple enough. So before I explain more, well, let me say, why do I call this the uncertainty principle? So what does it have to do with uncertainty principle from quantum mechanics? Well, nothing will change if I put an inverse Fourier transform on the right. The norm doesn't change. It's a unitary operator. And then you can see that if you think of functions on endpoints as wave functions of some quantum system, then this 1x localizes to the set x in position. So it just kills all coefficients. Somehow it kills all the entries in space that don't lie in x. If I look at this fn 1y fn inverse, this localizes to the set y, but in frequency. So it's a Fourier multiplier. So it kills all Fourier coefficients except those that lie in y. So you can reformulate this question rather easily as a bound on the localization on x of something whose Fourier coefficients lie in y. So you could write it, have a trigonometric polynomial with restricted set of coefficients, and then you take the L2 norm of that, but only over a potentially small set, and you want to know how big is this. So here I drew this blue localization position. So position will be horizontal for me, and frequency is red, and red is localization frequency. So that's why I call this the uncertainty principle. Again, it's a very natural question in a somewhat primitive setting, but turns out already rather hard. All right. So it turns out that some bounds you can prove. Well, first of all three operators here are bounded in norm by 1. One is unitary, other two are bounded by 1. So certainly this is bounded by 1 in norm. Also, if your sets x and y are reasonably small, you can actually get a non-trivial upper bound. And I call this volume bound, because what you do is you calculate the total volume of the intersection of these sets, x and y, So here you would calculate the total volume of the intersection of blue sets and red sets. So that's where a counterexample to this principle would lie. It would be localized both in position and in frequency on these sets. And then you divide it by n. So if you look at what this corresponds to the quantum in quantum mechanics, this tells you that no state can localize perfectly to y in frequency and to x in position, assuming that the intersection of these two sets, the total volume of it is bigger than Planck's constant. And so this volume bound is not very hard to show. It's, you can just use Holder and put L1 and L infinity norms here. And so it's a rather easy bound to see. It turns out that if you only allow yourself to use the sizes of these sets, this volume bound cannot be improved. So here's a basic counterexample, which perhaps not very surprising. What you can do is you can take n composite, and you can just take arithmetic progressions or dual subgroups inside of it. And then the norm here will exactly equal to 1, and that exactly agrees with volume bound. And in general, you can see that for other values of this number, also the volume bound cannot be improved if you only use the structure of these sets. I should say one other counterexample that I didn't show here, but maybe it's useful to keep in mind, is if I just took x and y to be arithmetic progressions, say of distance 1, so they're just all bundled together. And then you don't get an easy formula like this, but you see that modulo some exponential and n error, you will actually recover again that the bound will be sharp. So the rest of this talk will be about how to go past these two trivial bounds, 1 and the volume bound. So obviously, we will need to use something about the structure of our sets, and that's where the somehow hard parts will come in. All right. So before I do this, however, let me explain why this uncertainty principle is useful. And so how is it related to the spectral gap question? So I'll formulate this question in one of the classical settings, which is still wide open in the sense that we don't know, well, we know something. Well, we'll see in a moment. But it's still very hard to really understand what's going on there. So I'm just going to consider a convex co-compact hyperbolic surface. So it's a constant negative curvature surface, and it has these funnel ends, very big funnel ends. And then on this surface, you can consider what's known as resonances. Again, this is not really a talk about resonances, so I'll avoid talking about them too much. But there are a few ways of resonances. Perhaps the most classical way, and maybe the way most familiar here, is the poles of the Selberg zeta function. So you can write a zeta function from lengths of closed periodic of closed trajectories, and it has a meromorphic extension, and then the singularities of that will correspond to these resonances under appropriate normalization. So I should also say I will use a normalization where my unitarity axis, rather than real part s equals 1, which is if you work with automorphic forms, you're used to that, its imaginary part lambda is less than 0. So its imaginary part lambda is equal to 0. So another way to think about it, and that's where somehow the physical applications of this come in, is if I consider just the scattering resolvent. So if I consider the spectral family of the Laplacian on this space, it turns out that the continuous spectrum starts at 1/4. Again, it's kind of a classical fact. And then what you can do is you can, instead of considering z as your spectral parameter, consider 1/4 plus lambda squared. And what it does, it unwraps the place where the L2 resolvent was defined onto the upper half plane. Just by convention, I chose to be the upper half plane. And then a statement which is certainly non-trivial to prove. So it was proved in the works listed here. In particular, the work that I will mention will rely on the recent method of Vashi. You can see that this L2 resolvent, if you change your spectral parameter like that, it actually continues meromorphically into the lower half plane, and there it has poles. And these poles, modulo certain standard poles which have been understood, correspond to resonances. So these are the same numbers. Of course, this Laplacian interpretation tells you that you can actually, if you know something about these resonances, you can actually say something about decay of solutions to the wave equation for long times. Yeah, I'm not going to go too deeply into that, but I should say that these convex co-compact hyperbolic surfaces are a standard model case for understanding hyperbolic open quantum chaos. So you could have much more complicated situations where you try to study the wave equation, you're trying to define the resonances, And this is a model case for many such situations, because here, well, it's very hyperbolic. So it's very nice and explicitly written up in terms of what the stable, unstable decomposition is. This has uniform constant expansion rate and so on. So this is, when you look at a model like this and you think about decay of waves, you don't necessarily want to study waves on hyperbolic quotients themselves, but what you prove about hyperbolic quotients will tell you what's happening with more physical situations. For example, I don't know, scattering exteriors of 3 disks. All right. So here are some plots of resonances, so these poles. So here it's a bit hard to see. They are supposed to form, there's meromorphic continuation, so poles are supposed to form a discrete family. And indeed they do. It's just they're plotted for such a long time, for such a long real part, that in this particular case, these poles, you see here, they're kind of points, and then they just merge together. So this is just an artifact of the graph. These are actually, this is a plot of a discrete set of points. They just happen to.
What are we plotting here? I didn't quite understand.
These are the poles of this meromorphic continuation, or the poles of the Selberg zeta function.
Does the Selberg zeta function only, is that meromorphic or not?
Well, it continues meromorphically to the.
Yes, to the other side.
Right. And what I did here is the way people usually draw it. Maybe I should draw it once. People draw it like this. Real part S equals 1. Here it's holomorphic and has no zeros. And then you continue it this way, the Selberg zeta function. So I chose a convention that comes from the physical applications, which is this real S equals 1 becomes imaginary part equals 0. And my zeta function is holomorphic in the upper half plane. Because it's a more natural way of thinking about the spectrum of the Laplacian, if you want. And then you continue it to imaginary part less than 0. Of course, it's just a trivial rescaling.
The real axis is the unitary axis.
Yes, exactly. So the edge of the critical strip would be this horizontal axis. There are different rescalings and different methods because, yes. We don't know. There is a work of. There is some nice work of Tobias Weiss in a certain limit, which is the opposite of the high frequency limit that I'll talk about, and that it partially describes why, but in general we have no idea why.
So you're saying that the imaginary part, do I understand this correctly? As you vary the real part, the imaginary part of the is varying like this.
Yep. Yes.
He's saying it's just a discrete set of points.
Yes,
So
yes.
our eyes lie on a curve.
Yes, and of course what will happen is.
Okay.
What he's saying in order to show that
But it certainly looks like that, right?
It certainly looks like that. And in some sense it does, but it's a limit opposite of the one I'm going to talk about. So I'm going to talk today about the limit as you fix yourself in a strip, and then you let the real part go to infinity.
Okay, what are these L's you have up there?
Oh, these are the lengths of the neck. So this is the particular surface taken here was a 3-funnel surface like that. And L's are just the coordinates in the Teichmuller space of that. So if I changed 7, one of these 7s, only one, to be say 7.01, all of that will disappear.
I just want to point out that you'll never see anything like this if you were the Selberg zeta function of a compact Riemann surface. This I would be
No.
completely shocked.
Well, on a compact surface, you will see things which lie exactly on the axis. So this will not be a 2D picture.
No, there'll be a lot of stuff very near the axis.
Yeah.
Most of the stuff would be.
Oh, I mean finite area, yes.
But there will be.
So you're saying this is special for these.
This is special, and this is for me. This is just a pretty picture. I'm not gonna talk about why this is special.
If you change that 7 to something else.
So here I change the 7 to a 6, and then it just becomes something completely different. And then, for example, if I go to a torus funnel, then I will see, and I forgot to say this data is, this is not my data, this data was generously provided by David Borthwick and Tobias Weiss, and their papers have many more pictures like that and some explanations of why this is happening. But what I'm going to study is I'm not going to try to understand this very fine structure. Instead, I'm going to try to do something that will work for every surface, whether these numbers are rational multiples of each other or not. And I'm going to try to understand the high frequency limit. So I will consider myself in a fixed strip, which if you think about, say, the wave equation would correspond to considering fixed exponential rate of decay. And then I will take the high frequency limit this way.
So there seems to be a gap.
Yeah, so in terms of zeta functions, this is the familiar spectral gap question for the zeta functions.
The gap means I don't have anything except
Yes.
that I have a space there.
So I will formulate the question in a moment. But before I do that, I have to say also, I have to explain a little bit where do my sets x and y come from. So in the original question about uncertainty principle, I chose two sets somehow, and they depended on this large parameter n. Well, it turns out that these sets will be discretizations of what's known as the limit set of this quotient. So I can take the quotient, I can pass to its tessellation of fundamental domain, so to the covering space, and then I can consider points which do not lie in the infinite end of any fundamental domain. So this is a Cantor-like procedure. First I take out these 4 intervals, then I take out these 3 intervals, and so on. And then eventually I will end up with a closed set. And this is the limit set. And it's known to have, for all interesting cases, some non-trivial case, it has Hausdorff dimension between 0 and 1. And so this delta parameter will come up a lot in the future. So that's somehow that's the kind of set that I will be interested in as a model for my x and y.
So this is the Hausdorff dimension of a limit set under the orbit of the gamma?
That's correct. That's correct. So that's exactly that's the limit set. If you take any point and you take the fundamental group, then you take the closure of the orbit of this group intersected with the circle, you get exactly the limit set. Yeah, so that's a very classical object associated to this thing. So as I said before, I will be interested today when I talk about the surfaces in the essential spectral gap question. And so this question is it true that there is a certain strip which only has finitely many resonances? Of course, finitely many is not as good as no resonances. However, it's already, first of all, the methods that I will explain, they're high-frequency methods. So it's all limit real lambda goes to infinity, so finitely many in a compact set are allowed. And secondly, of course, if you, you'll see in a moment. I'll explain why finitely many is not such a big problem quite often. So if I talk about spectral gaps, not just essential spectral gap, but just what's the maximal imaginary part of the resonance? Well, this is given by Peterson-Sullivan theory. And so that's another classical theory that tells me that the topmost resonance is delta minus 1/2. And there are no, it's simple, there are no other resonances on this horizontal line.
The product converges absolutely onto that.
Yes, that's exactly, yes. That's in this case, that's one way to say it. So the convergence, for example, the Selberg zeta function would converge absolutely after here. Now, what this tells you is that you have a gap of size maximum of 0 and half minus delta. So I will explain a little bit. Perhaps. No. Is it possible to see here? So I will draw a picture like this. So here is my delta, the dimension of the limit set. Here is 1. Here is 1/2. So if delta is bigger than 1/2, my limit set is pretty big. And then Peterson-Sullivan gap doesn't tell you anything in terms of this asymptotic spectral gap question, because you already know that there are only finitely many poles above 0. Now, if delta is less than 1/2, then it gives you what we call the pressure gap. And it's given by this line here, half minus delta. Now, of course, I know that, for example, in this particular situation, if you manage to say that there are finitely many resonances in some strip past delta minus 1/2, then if you make a strip smaller, you will have no resonances except the first one, simply because they form a discrete set. All right. All right. So it turns out that this gap that I drew there is actually not optimal. So it was proved by Federic No in dimension 2 and Stoyanov and Petkov-Stoyanov in higher dimensions and a few other situations, that you actually have to have a gap a little bit bigger than half minus delta up to this point. The size of the gap, however, so this improvement on the size of the gap. So basically, how thin we can go until we hit the next pole here, even at high frequency limit. It's not particularly easy to extract from the arguments because they all, one way or another, they rely on the method originally developed in the 1998 paper of Dolgopyat, which takes advantage of small correlations, but it's hard to know what the epsilon actually is. And then there has been later work by Bourgain, Gambur-Tsarnak, and O. Winter, when you take a tower of congruence quotients and somehow prove uniformity in this. All right. So the goal today will be to try to understand this spectral gap better, to somehow get a spectral gap which beats the standard result and maybe gives you a bit more understanding on what this epsilon should be, or maybe works for delta bigger than 1/2. So with that in mind, here is a theorem that will tie this to the fractal uncertainty principle question. And so I will, that's one of the parts. I'll go through it pretty fast. So here is the statement. So this is joined with Joshua Zal at MIT. Assume that the limit set that I drew before satisfies a version of the uncertainty principle that I will refuse to write out, which is called the hyperbolic uncertainty principle. I will talk about what it is, with some exponent beta. Remember, we had this exponent there, this norm bound. Then you have an essential spectral gap of size, well, anything less than beta. And morally speaking, how would you prove this? Well,
the essential spectral gap means
eventually you will have nothing. And so the essential spectral gap, what it means, if I go back to relating this to the Laplacian, to the wave equation, it tells you that solutions to the wave equation should decay at the rate e to the minus beta t if they are high frequency. Now, at high frequency, solutions to wave equation lie along geodesics for bounded time. Now, if you go for long enough time, what you will see is that the stable unstable decomposition of the phase space will dominate. So you can decompose your solution as a bunch of things which exist for time logarithm of the frequency, which will start being very thin along the stable direction, and very thin along the unstable direction, very thick along the stable direction, very long. And then these small wave packets, as you propagate, they will turn into something still rather controllable, which will be pretty big along the unstable direction, pretty short along the stable direction. And so it turns out that in order to understand the exponential decay of waves, you have to face the following problem, that on each trapped trajectory of your flow, on each trapped geodesic, you can describe your behavior this way. However, the number of possibilities for a trapped geodesic will grow exponentially with the length of the geodesic. So it will grow like a polynomial of frequency, because I went to logarithmic time and frequency. And so the pressure gap, this gap, will tell you that if you just sum contributions from different trapped trajectories using triangle inequality in L2, then the growth of the number of trajectories, which is like e to the delta t, will not be as strong as the decay of your wave along each particular contribution, which is like e to the minus t over 2. And you get this. So here what we do is we instead try to understand, or how can we capture the cancellations between different trajectories here, which in general is a notoriously difficult problem because you have a long, long sum. And how do you know? You have this feeling that, OK, it should cancel somewhat, right? What are the chances they all have the same sign? But of course, one thing is knowing, feeling that they are not going to cancel, that they are going to cancel. And another thing is actually proving something like that. So this uncertainty principle, turns out, is a convenient way to encode these cancellations.
This number beta, which is obviously positive, is something you can estimate.
Well, that's what I'll talk about. Yes and no. So it's somehow, I will try to explain that this fractal uncertainty part, that's the most difficult part of the problem. I'm not going to claim that I conclusively solved the problem. But so what happens is, the way this reduction to fractal uncertainty principle works is you do this process for once. You started with somehow things which are which look like this. Then you propagate. then you end up with rectangles, which are very somehow long unstable, very thin stable. You do it for logarithm of the frequency because that's as much as semi-classical approximation lets you do. If you go thinner than h, then somehow your approximation doesn't make sense. But then you have to rewrite these horizontal rectangles as superpositions of vertical rectangles again. And so what the fractal uncertainty principle tells you is that how much of a norm you would lose when you do this rewriting. Because you have a superposition of unstable trapped states. When you write it as a superposition of stable states, most of them will be non-trapped. And then it will escape forward. And so the question is, when you do this process, how much of the energy still stays on the trapped states? All right. And so that's a very, very rough explanation of how this is supposed to work. Now, of course, I didn't talk about what this hyperbolic uncertainty principle is. It's something that can be written out. I mean, if you press me at the end, I can write it on the board. But I don't want to go there at this point. Something that can be written out very explicitly using just small neighborhoods of lambda gamma and a very explicit integral kernel. But in particular, what I will tell you is that if you look at the volume bound for this hyperbolic uncertainty principle that I drew before, this trivial volume bound, this will exactly imply the Peterson-Sullivan gap. So you can already recover the standard result using this way. And if I allow myself to lose a factor of 2 here, which depending on your regime you might or might not want to do, then you can reduce this hyperbolic uncertainty principle that I didn't write to a family of discrete uncertainty principles that I did write before for discretizations of this limit set in some sense. So somehow, if you understand certain discretizations of the limit set, how well they behave in terms of concentration with respect to discrete Fourier transform, then you can understand what happens in the hyperbolic set as well.
So the enemy for your uncertainty principle was some arithmetic progression.
That's correct.
You would be worried about arithmetic progressions in these Cantor sets.
Which don't exist.
Yeah.
So we will reach indeed arithmetic progressions in these sets. So, so indeed, the counter example that I had before was an arithmetic progression. But let me say a little bit more. So here is a very basic property of sets that come from discretizing these limit sets. You see, I really want to avoid to write out the explicit structure of this limits and discretization and so on. I claim that this is not very relevant, hopefully. But what we know in particular is that these sets are regular, so their dimension is very, very well defined. Specifically, if I go to discretization, so my x here is already a set of integers, I look at size n neighborhood of any point in x, the number of elements of x intersected this neighborhood grows like n to the delta with some explicit constant. So that, well, that's a definition. So that's a definition of what a regular set is.
What does this x have to do with the limit?
Right. So that's, you caught me here. So I will draw it once. There are actually two sets, x and y. I will draw one of them, and I'm not going to draw the other one. So here's your limit set, like that. Now let's say you took some small parameter alpha, and n will be alpha inverse, roughly speaking. Then imagine that I take any point in the limit set. I surround it by alpha size neighborhood. And here I flatten it out on the line, like that, this alpha size neighborhood. And I intersected it with alpha square times integers. Fattened by alpha square. So I discretize it. I have this set. I take an alpha square size neighborhood. And then I look what integers lie there. And so that's a set of integers. And that's what my x is. In a more primitive way, if you don't want to think about this additional neighborhood, you just take a piece of your limit set, somehow unfold it on the line, and then you look at alpha discretization, which is you just look at it on a scale of alpha, and you try to approximate it by a set of integers. So that's what you get. So the original sets were regular. Well, I mean, it has to do something. I will get to additive structure at some point, and it would be nice to understand what it actually has to do. But but that's what I did. Well, so yeah. So as I said before, the original limit set, it had a very nice dimension, yes? Yes, that is correct. I assume there are no cusps. Otherwise, this regularity property is false. So I know that my original limit set is regular with respect to the delta Hausdorff measure. And then when I pass to discretization, I get this notion of regularity. And I'm going to use this. And of course, the point here is that the constant C doesn't grow as capital N goes to infinity. So here is a basic conjecture. I don't know. It's certainly one of the statements that if false, it's probably much easier to establish than proving it. But here's a conjecture that if we have two delta regular sets, and we just consider this fractal uncertainty norm, then you always have an uncertainty principle for these with some exponent that improves over the standard one, so over the volume bound and over 0. And in particular, this conjecture, if true, would imply something that, well, people would probably find somewhat shocking in quantum case, that all hyperbolic surfaces actually have a positive spectral gap all the way up to delta equals 1. Of course, I have no idea whether this conjecture is true or not, but I should say, for reasons I'll explain later, all the counterexamples that I know so far, they are not regular sets. And in any case, if one were to disprove it, it would be nice to understand what kind of stronger assumptions to impose. So these sets, they're self-similar, but they're self-similar with respect to a hyperbolic group of transformations, which is much harder to somehow use. I should note, however, that if you considered the most basic class of regular sets, namely discrete Cantor sets, and not just discrete Cantor sets, but those given by this arithmetic formula, so you just allow certain digits base m, then the conjecture is true. So somehow, in a case where you can calculate something, the conjecture is true, but the reason why it is true, I will not explain really how this part works. It's not very hard. It's part of work in progress with Longjin.
I'm a bit confused.
But
your theorem seems to state something which is as strong as conjecture 1.
That's for Cantor sets.
No. Conjecture 1.
Which theorem?
The theorem, the main theorem.
Yes.
You say there's a beta which.
Yes. So the theorem says, assuming we solved the hard problem. So the theorem tells you that all the difficulty hides in proving the uncertainty principle.
I understand everything.
This statement says that if suddenly hyperbolic sets behaved exactly like linear Cantor sets, then we would be able to prove this. And there is some work in progress for random Cantor sets and so on. But there is a little bit more hope in trying to at least understand something about this, because this is a much more concrete harmonic analytical statement. So in some sense, we have more methods at our disposal. It probably won't be easy to, if this conjecture is true, to prove it. But nevertheless.
The only information you have on these discrete sets is this strong dimensionality.
Yes. Well, I have more information. I'm just not willing to put it in. That's correct. That's correct. Well, I think what will happen is somebody will disprove it, and then I would be very curious to see the counterexample. And then that will tell us something else about, the counterexample. Why doesn't it work for hyperbolic sets? So now let me just, talking about discrete Cantor sets, so this very special case, let me just flash one slide. So for discrete Cantor sets, you can calculate these exponents at least numerically, but I think this is a pretty good approximation from what I understand now. And here is our familiar plot. So horizontally is the dimension, which is log of the size of the alphabet over log m. The vertical is the exponent in the uncertainty principle. And then, well, I just did something completely silly. I just asked the computer to run all possible alphabets up to base 10. Just, in a few hours, it can do that. And here's the picture that we got. So you can see, well, I mean, there are some trivial parts of the picture. Like you cannot go to low dimension here just because there are no Cantor sets up to base 10 with this property. But you see that there are some sets which are pretty close to this half minus delta line. So this part, it doesn't seem that the conjecture is true uniformly, say, as m goes to infinity. There are some sets which come extremely close to this line, 0. None of them actually lie on this line. But this seems to be numerical, and also from the upper bounds that I was able to obtain. This seems to be polynomial in m as m goes to infinity. This is, so far I can obtain e to the minus m to the power m. And numerics show that it's at least exponentially bad in m.
So the theorem before that is not uniform for m.
Which one? Oh, this one, right. No. So this beta that you would get for a Cantor set will depend on the alphabet, and here are the beta.
And it's allowed in the conjecture.
It's also allowed in the conjecture.
So this is just for the model you had before. Right?
Well, in the conjecture, you should consider sets, with a fixed regularity constant. So I want it to be uniform in the regularity constant. Yes, sorry?
No, but that picture you had was for that.
That's for Cantor sets.
Your Cantor set.
For a very particular model. But for this model, you can actually calculate something and see, what's supposed to happen. And also, you can see that there is this gap near 1/2. Again, it doesn't seem to be uniform, but somehow the way our bounds deteriorate is not as bad when delta is close to 1/2. All right. So now let me see. I actually forgot what's the next slide, so we will find out. Very good. So the next slide, no, I did forget. I can talk until 4:05, right? It's 15 minutes. Okay. So the next slide will talk about how to somehow take advantage or partially explain the fact that near 1/2, at least for bounded m's, we seem to have a better improvement. And so this is where we get into additive combinatorics. So let's consider my original set X. It's a set of integers, mod n. And then I define its additive energy, which is just the set of solutions to this simple equation. Clearly, the number of solutions is bounded by size x cubed, because D is determined by a, b, and c. And clearly, it's bounded below by x squared, because a plus b is equal to a plus b is a solution. So the whole game of understanding this additive energy is somehow how is it closer to x squared or to x cubed, as the size of x is large. And then the importance of additive energy for this fractal uncertainty bounds comes in the following basic estimate, basic looking estimate. Namely, I can estimate this norm in the uncertainty principle if I know the size of one set and the additive energy of the other set. And then you have to think, for some time, what will this actually give you on this picture? But I will spare you that. I'll just draw a line. Well, what happens is if we have these delta regular sets, they have size n to the power delta. And then imagine that I managed to improve the additive energy by some power of n. So I managed to improve over the upper bound, over the maximal additive energy. Then we would get fractal uncertainty principle with this exponent. And this exponent will give you basically this, where this distance here will be the improvement that you got in additive energy divided by 4. 8 should be 8. Yes, so near 1/2, this number beats this should be 8. I'm sorry, I miswrote. But in any case, near 1/2, this line 3/4, 1/2 minus delta, if you shift it up, it can beat both this and that. And the way, you cannot, and even with the best possible bound on additive energy, you cannot say much. So how do you prove this statement? Well, here is my operator that I want to estimate. If I want to estimate its norm, it's the same as estimating norm of t star t, where t is the operator. Then I write out the matrix of that, and then I use Schur's lemma, which is just maximum over each row, the sum of values in over all columns. And then I get the following bound on the norm in terms of what? In terms of decay of the Fourier of the terms in the Fourier transform of the indicator function of my set. That's what it boils down to. Now, of course, I am not looking, you see, this Fourier transform, well, clearly I know what it is in L2, because Fourier transform is unitary. This is, however, an L1 bound, but it's actually much worse than that, because it's an L1 bound over a pretty small set. It's an L1 bound over this shifted set Y, which is rather small. So the moral here is that the Fourier transform on average cannot be too big because we know it's L2 norm, the Fourier transform of this thing. So if you take a generic point, it's not very big. But we're not summing it over all points. We're summing it over these special points. And it could just happen that the special points over which we sum will exactly coincide with the points where the Fourier transform is bad. And that's actually what will happen for an arithmetic progression. Now, however, you can get a better bound here if you allow yourself to use Holder's inequality by just using the number of points over which you sum and the L4 norm of the Fourier transform. Now, L4 norm of the Fourier transform of an indicator function of a set up to an explicit constant depending on n is exactly the additive energy. And so that's how the additive combinatorial invariant comes into this picture. So this is certainly, I hope this is not the most optimal bound possible in fractal uncertainty principle, but at least it tells you that if your delta was close to 1/2 and you knew something about a additive combinatorial invariant or additive combinatorial structure of your set, then you could get, you could grasp at least some of the cancellations happening. Now, well, of course, it's like infinite reduction. So now I reduced it to this combinatorial question, which is also quite hard. So I have to say, for general hyperbolic sets, obtaining a good bound on additive energy, somehow say even just running numerics, obtaining a good bound on additive energy is something I unfortunately still don't know how to do. Even though it sounds a bit ridiculous because these hyperbolic sets, they can be described by finitely many transformations. You would think this is a finite problem in some sense. But somehow it's still large enough that a computer doesn't seem to be able to actually do it. So, well, how do you estimate additive energy? Well, one thing that George Dahl and I were actually able to show is that if you have any regular set, you can estimate that the additive energy will have at least some positive improvement. And the size of the improvement depends only on the dimension and on the regularity constant. Unfortunately, this particular number is not particularly large. If you try to calculate it, this k is, well, Josh believes it's around 10 to the power 14. And so this gives you something that's mathematically, it's in principle nice in the sense that it tells you that as long as you have bounded regularity constant, the spectral gap that you will get for your hyperbolic quotient will actually be controlled. But it's probably not the best bound possible. Now, why is it so small? Well, this is because of the method of the proof. So I will actually do the method of the proof from the bottom. So I'll say that these regular sets, you can discretize them at a lot of intermediate scales. And then it's possible to show that if you have an improvement in additive energy on every scale, then these improvements compound and give you a power improvement. It's a little bit like, imagine you have a Cantor set. Why does the additive energy of a mid-third Cantor set, why is it smaller than the maximal additive energy? Well, just write everything in base 3. You say a plus b equals c plus d. You write every digit in base 3. And there are certain combinations of digits where a plus b minus c will have a 1 instead of 0 or 2. And then if you know somehow that on each digit there is some probability that you will have, you will fall out of your set, then you can compound that. Now, so all that you need is improvement on, you need an improvement on one scale. Somehow if you discretize far enough that you cannot have maximal additive energy. Well, this is where regularity comes in. There is a very basic argument using regularity that tells you that if your set has dimension less than 1, it cannot contain long arithmetic progressions, depending only on this regularity constant and or delta. The mid-third Cantor set doesn't have arithmetic progressions of length larger than 4, I believe, for example. For a general set, it's some constant. And then you can use Feynman's theorem from additive combinatorics, or rather a version of it due to, I believe, either Schoen or Sanders. I have to admit, I forgot which one we ended up using at the end, which tells you that if you don't have long arithmetic progressions, and you can make the statement more quantitative somehow, then you cannot have maximal additive energy on a fixed scale, and that's your improvement. However, all these general theorems from additive combinatorics come with this pretty large or small, depending on how you look at it, bounds. And so that's additive combinatorics is why we get such a small bound. It's in some sense because if you know your set on a sufficient large individual, in intermediate scale, if you know all the possible ways the discretization can work out, then you can compound that and you can get this energy estimate. And again, it's very feasible that for an explicit hyperbolic set, you should just be able to just list all possibilities in some sense. But if you don't do that, then you resort to doing something that's true for general sets, and that's where this comes in. Now, finally, let me give a few numerical pictures that will show why I believe that this additive energy is actually much better than this weak upper bound. So here, instead of plotting additive energy, I will do what I call an additive portrait. So I just look at each number in Z mod n, and I say how many times does it come up as a difference of pair of numbers in my set. And then I sort these numbers in decreasing order, and the additive energy, as you can see, is just the sum of squares of these numbers. Because A minus C is equal to D minus B, and then you just loop over what's this A minus C. That's J. Now, and this tells you a little bit in more picture form what's happening. So for example, here I took a subgroup. So basically, yeah, the subgroup here. And then here are my additive portrait, unsorted. So of course, if you are divisible by 16, you get a lot. Otherwise, you get nothing. Then I sort it. I get something like that. The L2 norm of that is pretty large. So additive, arithmetic progressions or subgroups, they have maximal possible additive energy. Now, I could take a completely random set just to see what will happen. Of course, it bears no direct relevance to the problem, I should say. But just to see what's somehow the best thing to expect. And then you would see here a Poisson statistic. This is 1, 1, then 1/2, then 1/6, 1/24, and so on. So that's pretty good. That would give you somehow additive energy very close to the minimal one, which is x squared. Now, here is what happens if you take an actual hyperbolic quotient. Here, I think we took lengths of next 5.2, 5.2, 5.2, so the dimension will be close to 1/2. So here we discretized it on a scale of 2 to the minus 16. Here's the set. Looks roughly Cantor-like. Then you draw the portrait, and then you sort it like that. And then what you see is that it lies quite closely on the graph of the function 1 over square root of j. Yeah, this is not something you can, well, I can prove at this point. But this is at least something that it's one of these things that, it's true. Just can't prove it. And then here I took an actual Cantor set. And you see that exact Cantor sets, they actually have worse additive energy, as expected, because they have a lot of somehow rigid, left half is exactly a copy of the right half. In some sense, the sets that I drew numerically, they behave like randomized Cantor sets. And so that's these numerics let me formulate the following conjecture, that the additive energy should actually be improved, not only with some positive improvement, but with exponent which is basically the maximal possible, which is minimum of delta and 1 minus delta. So if right here my points lie exactly on the red line, then my additive energy, if I sum the squares of these, would be n squared log n, or sorry, n log n, which would be like size x squared. And so in the final slide, I will show what will happen if one is able to actually prove this conjecture. I should say that this conjecture, for a given surface, it's a much more realistic thing to try to estimate this additive energy. In some sense, it's a finite question. If you fix the generators, it should be, for an exact Cantor set, you can just estimate it by hand, its eigenvalue of some matrix. For hyperbolic sets, it's harder, but it should still be possible. And so if we knew something about additive structures of our sets, then we would get the following picture. So this final graph, this is the spectra of 1/2 and 1 that I drew there. And this red is where the conjecture would take you if you wanted the gap. And the green dots are the numerically computed spectral gaps for a few families of convex co-compact surfaces done by Borthwick and Weiss. So at this point, I shall conclude. Thank you.